Hi, so today I'm going to talk about the Compton wavelength. But before that, let's start off with a basic frequency 101. So, frequency equals to cycle over time. Basically, the ratio of how many cycles you completed over the time it takes to complete those many cycles. It is equal to, in mathematical definition, 1 over t, where t is the period. And what it basically means is one cycle, and it took t time to complete. And one cycle takes a period of time to finish. So, there are other ways to write the frequency, which I'll show here. Omega equals 2 pi over t. 2 pi is, because omega is defined as angular frequency, so 2 pi is how much in radians of a cycle. So one cycle equals 2 pi. And we could rewrite this by dividing 2 pi on both sides. Omega divided by 2 pi equals 1 over t equals f. Splendid. How about velocity? Can we relate velocity with frequency? We can, and I'll demonstrate this right here. So, if I have a function, like a wave, travels like this, it moves like this, a sine wave. The distance between this point and this point, these are two peaks, it's called a wavelength. This is a wavelength. And the wavelength is often denoted as lambda, so it equals to lambda. Notice that this wave on top is equivalent to this wave on the bottom, to this portion of the wave on the bottom. And these 2 points, the ones I'm drawing axes to, are the distance covers the entire period. Basically, if this is 0 and this is some arbitrary number phi, this is basically the distance that covers a period. If you notice that this is 2 pi of a sine wave. So, it takes t time to travel this much distance. So v equals lambda over t. That means v over lambda equals 1 over t, which equals f. Okay, so we have our frequency equation. So frequency equals to f equals 1 over t equals to omega over 2 pi, and it equals v over lambda. Okay. And one of the special wavelengths in physics is called the Compton wavelength. And the Compton wavelength requires a famous equation. You might notice E equals mc squared. And what does E equals mc squared mean? Well, imagine you have a block. A block on the table. It has velocity 0. You may say it has no energy. It has no kinetic energy. It's on the floor. It's no energy. But it does have a rest energy. So the rest energy is equivalent to E equals mc squared. So if this block has a mass of m1. The rest energy of it, where there's no velocity at all, no kinetic energy, it still has energy, is equal to m1c squared, the equivalence of mass and energy, as Einstein derived. So the Compton wavelength relates this equation. So the Compton wavelength, we call from the photoelectric effect, photoelectric effect. That the energy of the laser, or like a beam of light, is equivalent to E equals h times f, the frequency. And E, the Compton wavelength, is defined when E is set to mc squared. And recall that frequency is equal to, as shown here, v over lambda. So mc squared equals h times v over lambda, which v equals c. It is set at v equals c. And mc squared, mc squared equals h c over lambda. And if we reorient this, lambda c, which is how we denote the Compton wavelength, equals to h over mc. This is the Compton wavelength. Notice that it's basically a definition. It is when a particle traveling at its maximum speed with its rest energy. And you may say how it only has its rest energy because there's no kinetic energy whatsoever, and v is set to c. This is actually an intrinsic property of any particle. And if you get smaller than this wavelength or greater than this, well, if you get smaller than this wavelength, that means you have to go beyond the speed of light. There is destruction or creation of particles, which requires quantum field theory, I believe. Not going to dive into here today. So I'm now going to talk about Du Bois. Wavelength. Derivation for photons. Okay, so for photons travel at high velocity, so we need to use relativistic equations here. So E, the energy, equals mc squared over 1 minus v, the square root of 1 minus v squared over c squared. Similarly, P, the momentum, equals mv over the square root of 1 minus v squared over c squared. Okay. And let's just, okay, and the goal here, the goal is to find an equation that can relate E and P, the energy and momentum. And we can do this, but first we square both equations. So step one is to square both equations that we have up here. Basically squaring E and P. So let's denote this as equation 1 and equation 2. So for equation 1 right here, E squared equals mc squared 1 minus v squared c squared. Sorry, that's here. Sorry, I did not square above. m squared c to the fourth, that which can be simplified into m squared c to the sixth, where we c squared minus v squared. And 2, p squared equals m squared v squared c squared minus v squared. Great. So now we need to relate 1 and 2. So e squared equals to m squared c to the sixth c squared minus v squared, which equals to m squared v squared c squared minus v squared times alpha plus phi. Maybe I should use a different color for this. Alpha plus phi. And alpha and phi are combinations, some combination of the mass and speed of light. So when alpha equals to c squared and phi equals to m squared c to the fourth, we can get a relationship between E squared and P squared, the energy and momentum. So notice that E squared, we have this right now, which equals to m squared v squared c to the fourth, we multiplied alpha, c squared minus v squared, plus m squared c to the fourth, but we multiplied the top and bottom by c squared minus v squared. Okay, divided by c squared minus v squared. That way, if we only look at this side, we notice that of course we have v squared, m squared times v squared times c to the fourth, plus m squared c to the sixth minus m squared c to squared v squared. Okay, that's c to the fourth. Sorry, that's c to the fourth divided by c squared minus v squared. And notice that this term and this term right up here, these terms, they cancel out. So what we are left with is m squared c to the sixth divided by c squared minus v squared, which is equivalent to e squared. So in the end, the final equation we have is e squared equals to p squared. Notice before we squared p, and then we're multiplying it by c squared and adding 5, which we defined it to be m squared times c to the fourth. Okay, we have this equation. Okay. Now, for photons have m equals 0. They have no mass. They have momentum, but they don't have mass. So E squared equals to P squared C squared. That's what we have. And we square root both sides. E equals P times C. And remember, E for a light wave equals H times F. HF equals to P times C. And recall that F is V over lambda. You see up there? F equals V over lambda. So H times V over lambda equals P times C. And notice that photons move at the speed of light. So V is equal to C. H times C divided by lambda equals P times C. Cross out both the C's. move lambda to the right, multiply lambda on both sides, and divide the p, the momentum. H over p equals lambda, which is better if we write it this way. Lambda equals h over p, and that is the Broglie wavelength, which works for matter waves too. There's a more conceptual explanation for this, which I'm not gonna dive deeper here, but this is for photons, and this is how it's derived. Thank you.